Yumi Hirano from NEC Corporation, and I would like to, before my presentation, I would like to tell you about my short biography, and this is a. Can I use a pointer or this one? And off.
Doesn't work.
Doesn't work?
Well, it's a high-tech one that goes through it's a, you move that thing inside, it's not a laser thing. You can still use it.
Okay, he will get a laser thing first.
Okay, I try. And this is my first project in NEC Corporation, and this is a cell phone for 3G and wireless LAN phone, and for the NTT Docomo. NTT Docomo is a carrier company in Japan, and I was a member of this project, and my part area was QoS and power saving protocol in for wireless LAN VoIP, and it was called UA. Thank you so much. This is a UAPSD is specified in IEEE 802.11e, and when we use this protocol, and the performance depends on the parameter of the wireless LAN. So we evaluated this protocol and proposed the optimal parameters to the development division. And the addition, I attended Wi-Fi Alliance meeting in order to add the protocol that our implemented in our products to the test plan items. And this is a first project. And this page shows our my current project. And the first project is Future Internet project in my laboratory. My laboratory has a big future internet project, and I'm also a member of the project. And I'm discussing with Professor Suda in is study on interaction between TCP and wireless. This is today's topic. New flow level QoS function for wireless LAN. And then anyway, I move to today's topic. The title is Evaluation of Packet Loss on Throughput Unfairness between TCP upflows over IEEE wireless 802.11 wireless LAN. Please interrupt when you have a comment or question. Let me start with background of my topic. Recently, we often use wireless LAN because mobility, and we can get mobility, high throughput with lower cost. And on the other hand, the direction of traffic is mainly downlink, and the used transport protocol is TCP. However, we expect that the uplink TCP traffic will be increasing because we can get opportunities to become a source of information, such as video conference, P2P communication, and synchronized communication, and so on. And in this condition, we have interest interest in whether we can get the enough throughput for each flows, each uplink TCP flows. In response to this question, there are some researchers. They pointed out that there is a serious unfairness problem. The problem is illustrated in this figure. There is a extremely low throughput flow is generated in this situation. But however, they didn't take care of the wire network. So therefore, I will show the evidence that when we consider the wire network, there is a not so serious unfairness problem. And this page shows the unfairness problem that past works pointed out. This is a throughput for individual uplink TCP flows. They evaluated this condition while each wireless station continues to send TCP data packets to the receiver. So that there is only uplink TCP flow condition. And the receiver sends back TCP ACK packets to the wireless station. However, the wireless media bandwidth is much lower than wire network. So the TCP ACK packets are accumulated at access point, and TCP ACK buffer overflow easily occur. And this is a not short-lived phenomena. It's a long-term. This situation remains in long-term, and I will explain in this graph. The unfairness causes by the interaction between burst loss of ACK packets and overflows. So this is because generally TCP increase window size and throughput as long as TCP sender gets ACK packets, and like this figure. However, if all the ACK packets are lost, the timeout occurs and it results in minimum window size. It means the decrease of throughput, like this figure. So, and small window flow is very sensitive because the all of the ACK packets are discarded, and which result in minimum window size. So this difference causes the unfairness. However, we doubt actually this unfairness happen because they don't care of wire network. So this is a problem statement. Past research didn't care about the packet losses in the wire network. In fact, there are packet losses in somewhere in wire network. So, and when we consider packet loss at wire network, we expect there is much less unfairness.
So the loss in the wire network is due to buffer overflow?
Yeah, buffer overflow. So and when we large flows, for large flows, large flow doesn't suffer from buffer overflow because the when we at least one packet arrive at the sender, the flow can increase window size, and the large flow can steadily increase windows. So is that okay? So, and we expect that there is not so serious unfairness in this situation. So why when we consider packet loss at one network, we can get more fairness, and this is a change of window size in both case of no loss and loss situation. And please see a right hand graph. This shows the change in window size when we have packet loss at one network. All flows suffer from packet loss, and the window size change with fluctuation like this. So in the long period, they have the roughly same throughput. So I think there is not so much unfairness. This is a research objective. We would like to show how much does the fairness increase in case of packet losses in the wide network. This is an evaluation model, and the model is same as past works, but the new point is packet loss which range from 0 to 5% are inserted. And wire stations continue send TCP data packets to the receiver, and buffer size is 100 packets.
Did you use legacy random?
Yeah. Why? Legacy random.
You didn't use SAC option.
We don't use SAC option. And this is the results. And this shows the fairness of the each flows. And x-axis is the packet loss rate of data packet. And y-axis shows the degree of fairness. This is called fairness index. And larger fairness index means more fairness, and smaller fairness index means less fairness. So, and the fairness index equal 1 means all flows has completely same throughput. And please have a look at this red plot. This is a fairness index, and this plot sharply increase according to increase of packet loss rate, and at the 0.5%, the fairness index increased to 1, and at larger than this point, the fairness index remain same value. And on the other hand, this blue line is the aggregated total throughput of the wireless system. This total throughput gradually decrease until 3%, but at larger than 3%, the total throughput largely decrease. And so this is a control. This is a cost for the packet loss. And I would like to say from this graph, packet loss reduces unfairness. Okay.
So why do you have unfairness and you have no loss in the binary? Because you have 100 packets of buffer size that you drop at the end.
Yes, and when we
And how is that loss process defined? Is it like select? Is it biased towards one of the flows?
I'm sorry.
Like, is it like, are you dropping X from both flows on average, on long-term average equally?
Yes, but the all flow has suffered from packet loss, but the overflow doesn't occur.
Overflow what?
All flow suffer from overflow, packet loss caused by overflow.
Okay, I was trying to figure out why it's different from one flow to the other.
Sorry.
I would expect if there's a drop process for X, the cumulative system would probably drop.
Sorry, and sorry, I can use this page. And when we have random packet loss, we can have this fluctuation and increase in window size and decrease like this figure. But
This is loss in the wire network. Or the
wire
access point?
network.
My question is probably on the other side.
This one.
If you have no loss, right?
Mm-hmm.
And why did we have the unfairness to begin with?
This is caused by only overflow. So small flow suffer.
How is the flow side defined? What is small flow? Is it like you have less, they're not of equal demand? Are they sending the same packets per second? When you say small flow, is it one traffic demand is smaller than the other?
Small flow mean the. I want to say if once a timeout occurs, the difference between other flow keep the same value. Do you understand? So, and for example, at first 10 window size is 10, and the packet loss occurs and timeout, and the window size decrease to 5, and the 5 flow is very sensitive to the overflow packet loss because all those packets are easily discarded.
So you're saying whoever is losing the first packet is going down?
And first packet for TCP, and at least one packet is okay to increase window size.
Actually, my question is about simultaneous. So what causes those two flows start from different points?
I'm sorry.
What causes two flows start from different TCP size? One flow starts from high window size, the other one starts from low window size. What causes it?
This is caused by for example, retry timeout, retry out, or the packet loss caused by phasing.
Not starting point. That's a starting point to sending the flows. Both flows are started to be sent at the same time in this equation.
So my question is, if two identical stations start sending same amount of data to the uplink, what causes they have different window size? Maybe channel or
Yes, in the channel, but when but channel is a usual condition. So in the bad channel, the packet loss is okay. The TCP decrease the window size and throughput. And once the TCP decrease the throughput, the difference between other high and low throughput, it is very difficult to explain. But so when it happened to the decrease in TCP window size, the difference between high throughput and low throughput window will increase, and it keeps in long time.
so their request for the transmission is identical.
Yeah.
Or somehow you happen to have a different window size.
Yes. So the reason of the start point of the reason to decrease in throughput is in the wireless media.
Maybe they didn't start at the same time.
So, yes, it is difficult to explain. Is it okay? Where I did.
So how do you define fairness index?
Pardon?
How do you define fairness index?
Fairness index. Fairness index means is the
It's a large. Is that the Jane index or the same?
Maybe he wants to know the definition.
definition.
For fairness index.
Yes.
Oh, it was a I have.
Is that the famous definition? Famous one?
Oh yeah, right. Oh, sorry, I don't have the formal formulation today, but the so when we have a same all flow has the same throughput, its fairness index is 1, and we only one flow has a 100 megabps, but the other flow has 0 megabps. It is extremely 0. This is a fairness index. I will show you the formulation later. Can I move to the next slide? Okay. And this is a relationship between fairness index and number of flows. X-axis is packet loss rate, and Y-axis is fairness index, and same with the last graph. And blue line is result for 5 flows, and pink line for 10 flows, green line for 20 flows. So you can see that larger number of flows has lower fairness index. So larger number of flow has more unfairness. Because the number of ACK packets will increase, and so the buffer overflow easily occurs. So, and we can say number of flow increases unfairness. And next slide shows relationship fairness index and buffer size at access point. And the format is same as last two graphs. And the blue line shows 50 packets, and pink line shows 100 packets, and green line shows 300 packets. And if when we have smaller buffer size, we have more unfairness. So this is a smaller buffer size easily cause the buffer overflow of ACK packets. So we can say smaller buffer size increases unfairness. And this
the buffer size is the for ink access point or terminal?
Access point.
So it's a buffer on the downlink, essentially.
Yes, buffer of the downlink. And yeah, in this situation, the downlink packet is only ACK packet. And I move to summary and conclusion. And the past works pointed out that there is so serious unfairness, but however they don't care about wire network and the packet loss at the internet. So we evaluated this situation again with packet loss, and at more than 0.5% packet losses, unfairness doesn't occur. So we can say in the real situation, no special controls are needed against throughput unfairness between uplink TCP flows over wireless LAN. Thank you.
So what are the typical packet losses?